Welcome back. We returned to our previous example where we were looking at a 3 by 5 matrix. In the last example we found a three-step process to produce the null space of A. In this case we're going to show how we can use the same steps to find the linear dependence relation in the columns of A. In particular, if we start with the original description of matrix A, our first step to find the linear dependence relationship is identical to what we did before. In particular, we're going to find the RREF of A. We do this via elementary row operations or multiplication with elementary matrices, or we can use a calculator. In this case, we know that the corresponding reduced row echelon form is given by the 3 by 5 matrix that we calculated in our previous example. We immediately identify the pivot columns and non-pivot columns. In this case, we see immediately that columns 1 and 3 are pivots, and using our stair-step structure of the RREF, we see that columns 2, 4, and 5 are what we call non-pivot columns. We know that there are 5 columns total, and as we discussed before, this is the 2 pivot columns plus the 3 non-pivot columns. What's really nice about this structure is that we can immediately conclude from the structure of U a lot about the linear dependence relationships on the columns of A. In particular, the pivot columns of U identify what we call the linearly independent columns of A. So in other words, the set including the first column of A and the third column of A is a linearly independent set of vectors. On the other hand, the non-pivot columns of A the non-pivot columns of U are identical to the non-pivot columns of A, and these identify the linearly dependent columns of A. The way you can think about this is here, when we have this stair-step structure in the RREF form, the pivot locates linear independence, so new information not contained in the previous columns. When you have this elongated stair, what that indicates immediately is that each of the new columns is a linear combination of the columns before that. Here we see that -2 times the first column produces the second column. The same exact structure exists in A. If you take this first column of A and you multiply it by -2, you get the second column. There's that stair-step structure. Let's try the third the fourth column, which is the second non-pivot. If you take -1 times the first, 2 times the second pivot, you would get this column. Well, guess what? By the structure of RREF reduction, the same linear dependence relation exists within the columns of A. In other words, -1 times the first column plus 2 times the third column, which is the second pivot, is equal to the fourth column. Let's write those down so that we can capture that. Using the information that we see in the RREF form, we're going to relate those back to this. So we see immediately that in the RREF form of our matrix, maybe we need to cover this up for a minute. So we're still in step 3, which is to recognize the non-pivot columns as identifying linear dependent relationships. We see immediately linear dependence number 1. The second column of U is equal to -2 times the first column. Nothing major going on here. We could write this in vector form that just says -2, 0, 0 is equal to -2 times 1, 0, 0. But the major claim that we're making is if this linear dependence relationship holds in U, the same one holds in A. In particular, we know that the second column of A would be -2 times the first column in A. We could write this using colon notation. The second column of A is -2 times the first column of A. Okay. That took care of this one. We go down to the next stair step. This is linearly independent because it's our pivot. Here we see that the second linear dependence relation is given immediately by the fourth column of U is a linear combination of the two pivot columns. Two times 1, right? For longevity's sake, let's go ahead and list out the statement that was made as a vector. This is the last time I'm going to do this in this video. The audience is encouraged to write this down for yourself. Using colon notation, just actually physically write down exactly what's stated here. Not very deep because of the structure of RREF. The major idea of RREF, however, is the same linear dependence relationships that exist in the RREF form, U, also exist in the original matrix. And this is a deep and fascinating, dare I say, fact about the elementary row operations that we chose to use to reduce our matrix. Let's go ahead and check this. This is the, oh sorry, I guess this will be the last time that I write this down. We have -3, 1, 2, and then I add that to 2 times the third column, which would be -1, 2, 5. And indeed, of course I made a mistake here. This should be the fourth column of A. The fourth column of A, if we look back at the original matrix, is not given by this thing. Sorry about that. The fourth column of A is given by 1, 3, 8. Right? Because if we look back at our original matrix, the fourth column is 1, 3, 8. Right? Now that makes us feel a lot better because 3 minus 2 is 1, -1 plus 4 is 3, -2 plus 10 is 8. The last linear dependence relation, instead of writing all this out, we can immediately jump to the end result and we see that 3 times column 1 minus 2 times column 3 would be equal to column 5. Column 5 is going to be 3 times column 1 plus minus 2 times column 3. This is the exact same process that we used to generate the linear independent vectors that span the null space. I wanted to put an emphasis on the idea that RREF, the stair-step structure of RREF, is actually a method to identify very quickly which of the columns of A are linearly independent, which of the columns of A are linearly dependent, and how can you ascertain the dependence relationship between those. Okay, see you in the next video.